Hello all, welcome back to the YouTube channel The Engineering Surveyor. Today I am going to explain how to do a total station traversing using double phase method. Especially I will explain how to do a closed link traverse using a total station. So first we look at the ground and the area where we are going to survey. So as you see in this figure, we are going to survey the road starting from 9002 and 9003 control points and ends the survey from 9007 and 9008 control points. These 9002, 3, 7 and 8 are the standard codes that we are going to use to identify the control points. So these 9002, 9003, 9007 and 8 were established using DGPS, or we call a global navigation positioning systems, and we are going to use them throughout the project to collect the details. And the lines joining these control points are known as control lines. So the first line joining 9002 and 9003 control points can be considered as control line 1. Then to collect the details, we need to establish traverse stations in between these two control lines. So as you see, because of this bend and the terrain, we can't see the intermediate locations in between 9003 and 9007. Therefore, we need to establish traverse stations in between 9003 and 9007. So 9004, 9005, 9006. Likewise, we can establish 3 traverse stations between 9003 and 9007. So these are known as traverse stations until the survey is completed. So once the survey is completed and once we find out the coordinates, they will become secondary control points. All these control points which were established by DGPS are known as primary control points. And computing the error, these traverse stations will become secondary control points. And these lines joining the traverse stations are known as traverse legs. Now we'll see how to measure an included angle using double phase method. So we can set up the total station at 9003, then we can target to 9002 and we can set the horizontal angle as 5 degrees. So you can either take 1, 2 or 3. It depends upon your choice, but I prefer not to select 0 because it is very difficult to do the calculations in some instances. Therefore, always take a positive value, but don't take more than 10, right? So I prefer if you can choose between 0 to 10 angle value. So I prefer and I chosen 5 degrees as the phase left reading when I'm observing from 9003. So then I can record it in the left column. So the line is 9003, 9002. Then I'm going to turn the telescope clockwise and target to 9004 prism. So I can record it at the second row. So the line is 9003, 9004. The phase left angle is 135.11 minutes and 54 seconds. So then what I am going to do is I am going to transit the telescope about the Trunnion axis and get the phase right reading to 9004 again. So it is 315.11.44. So this is how I record it in the second row and third column. The phase right reading 315 degrees 11 minutes and 44 seconds. Then I'm going to look back the 9002 from phase right. So it is 184, 59, 43. So I can record it in the phase right column 184 degrees 59 minutes and 43 seconds. So that is how I record it. Then thereafter what we need to do is we need to find out the distance from 9003 to 9004. So usually this distance can be taken from total station by pressing HD button. So when we press the HD button, we can get the distance. The measured distance was 68.788 meters. So we can put it in a separate column after the reduced angle column, and we can record it. So we don't need to find out the distance from 9003 to 9002 because it is a control line. So since we know the coordinates of 9002 and 9003, we can calculate it using the coordinates. So what we need to do is we need to find the distances in unknown lengths. So now we will see how to get the mean value for 9003, 9002 line. So that we can get the addition of phase left reading plus the deducted angle of phase right reading. So we need to deduct 180 degrees from phase right angle because when we transit the telescope about the Tunisian axis, the angle difference was 180 degrees. So we need to deduct that 180 degree from phase right reading. So then we have to get the average of phase left reading and phase right reading. So it is just like this: 5 degrees plus 4 degrees plus 59 minutes and 43 seconds and divide it by 2. So then we can get the mean value of 4 degrees 59 minutes and 51.5 seconds. So we can record it in the mean column for the line 9003, 9002. And similarly, we can find out the mean value for 9003, 9004 line. As you see, the phase left reading is 135, 1154 for the 9003, 9004. And it should be exactly more than 180 degrees from the phase left reading, but actually what has come is 315, 1144 instead of 315, 1154. So therefore we need to get the mean value. So first we need to reduce 180 degrees from phase right reading and get the average between phase left reading and the reduced reading of phase right. So this is how we get it. We need to deduct 180 from the phase right, then it will become 135 degrees 11 minutes and 44 seconds, and we need to add it to the phase left reading and get the average. So it is 135 degrees 11 minutes and 49 seconds. So we can record it in the mean column. So we then we can find out the reduced angle. The reduced angle is the difference between these two mean angles. So we can reduce the mean of 9003, 9002 line from mean of 9003, 9004 line. So the difference is 130 degrees 11 minutes and 57.5 seconds. So we can put it in the reduced angle column. And then we can mark it in the figure 130 degrees 11 minutes and 57.5 seconds like this. Then next thing is we need to find out the included angles of all the stations. Next we are going to find out the included angle between 9003 and 9005 measured from 9004. Again we can set up the phase left angle to 9003 as 5 and carry on the procedure as similar to previous one. Here, so the phase right reading of 9004, 9005 reading is less than 265.57 minutes and 0 seconds. In that case, the meaning of this 85 degrees 56 minutes and 44 seconds is it has rotated full circle of 360 degrees and has rotated more 85 degrees 55 minutes and 44 seconds. So the actual value of this phase right reading is, you need to add 360, then the value is 445 56 44 seconds, right? So from this 445 degrees 56 minutes and 44 seconds, you have to deduct 180. When you are deducting 180, you will get 265 56 and 44. So you need to get the average of phase left and phase right, then you will get 265 56 minutes and 52 seconds. That's how you do the calculation in this case, right? So even though it is 85, don't put 85. The meaning of 85 is it has rotated more than 360 and more 85 degrees. So the actual value of this 85 is 445. from that 445 you have to reduce 180 degrees and then get the average between phase left and phase right. So then you will get the mean value of 265 degrees, 56 minutes and 52 seconds. So the reduced angle is 260, 57 minutes and 0.5 seconds. So this is how you are going to put it in the figure. So similarly, we can find out all the included angle like this for 9005 station, for 9006 station, and for 9007 as well. And this table shows the completed included angles found after doing the total station traversing. At the same time, you need to find out the distances of all these legs as well. The next thing is now we'll see how to find the whole circle bearing to a start control point. So what is the meaning of whole circle bearing? The clockwise angle measured from north is known as the whole circle bearing. So we have the coordinates of 9003 and 9002. So we can draw this 9002 and 9003 according to the coordinates as you see here. The coordinates of 9003 and 9002 can be written near to these control points in the figure, and then we can find out the delta N, the north in difference, and delta E, the east in difference. So according to the figure, the theta can be calculated. So the WCB to 9003, 9002 line is 180 plus this theta. So the WCB is the clockwise angle measured from north to the control line. So it is 180 plus theta. So we can find out the theta using tan theta equation. So the trigonometric equations. So tan theta is equal to delta E upon delta N. We can find out the delta E easily by deducting the easting coordinate of 9002 from the easting coordinate of 9003. At the same time, we can find out the delta N by deducting the northern coordinate of 9002 from the northern coordinate of 9003. So the tan theta value is 0.172233. So when we get that tan inverse value, the angle for the theta is 9 degrees, 46 minutes and 20.54 seconds. So the WCB is 180 plus theta. So then we can find out the WCB very easily. 189 degrees, 46 minutes and 20.54 seconds. So then we can mark it in the figure like this. So the next thing is finding out the WCB to 9003, 9004 line. So this is again I will tell you the clockwise angle measured from north to 9003, 9004 line is the WCB for 9003 4 line. For that we can add the included angle measured from 9002 to 9004 from 9003 to the WCB of 9003, 9002 line. So easily we can get the angle from north to 9003, 9004 line. It is 319 degrees, 58 minutes and 18.04 seconds. So similarly, we can calculate the whole circle bearings or WCBs for other lines as well. So we'll try to find out the WCB for 9004, 9005 line. So this is kind of a easy method to find out remaining WCBs of this traverse. So what we need to do is add the included angle at the station to the WCB of previous line. So the previous calculated WCB is 319 degrees, 58 minutes and 18.04 seconds. So we need to add that to the included angle of 9004 station. So that is 260 degrees, 57 minutes and 0.5 seconds. So when we add it, so we can see the addition is 580 degrees, 55 minutes and 18.54 seconds. So if the sum obtained is below 180, then add 180 to it. But we can clearly see that 580 degrees is greater than 180 degrees. Therefore, it is not applicable. Then if the sum exceeds 180, then deduct 180 from it. That's okay. Why? Because the 580 degrees is greater than 180 degrees. So therefore we can deduct 180 from 580. Then the value is 400 degrees, 55 minutes and 18.54 seconds. Then if the sum deducted value is less than 360, then accept that angle as the WCB. But the sum deducted value is greater than 360, therefore it is not applicable. If the sum deducted value exceeds 360, then deduct 360 from it. And clearly this 400 degrees is greater than 360 degrees. Therefore we can deduct 360 degrees from 400 degrees and get the value 40 degrees, 55 minutes and 18.54 seconds as the whole circle bearing to 9004, 9005 line. So we can mark it in the figure. Then we can determine the WCB of a line at a station. So then we can determine the WCB for line 9005 and 9006. So again, similarly, we have to add the included angle at the station to the WCB of previous line 9004, 9005. So the previous WCB is 40 degrees. Now we are going to add the included angle of 9005 to that 40 degrees, that is 223 degrees. So the addition is 264 degrees, 49 minutes and 22.54 seconds. If the sum obtained is below 180, then add 180 to it. But clearly we can see it is greater than 180, so therefore it is not applicable. If the sum exceeds 180 degrees, then deduct 180 degrees from it. So clearly, since it is exceeding 180 degrees, we can deduct 180 degrees from the calculated 264 degrees. Then the value is 84 degrees, 49 minutes and 22.54 seconds. If the sum deducted value is less than 360 degrees, then accept the angle as the WCB. So we can accept it as WCB. Since it is less than 360, we can accept that angle 84 degrees, 49 minutes and 22.54 seconds as the WCB for 9005, 9006 line, and we can mark it in the figure like this. Similarly, we can calculate all the WCBs for the lines starting from 9003 to 9008. Then the next thing is finding the angular misclosure. So we know that we need to end the traverse from a non-controlled line. So that line is 9007, 9008. So we can find the actual WCB to 9007, 9008 line. For that we can mark the north like this and the angle beta like this. We can write down the coordinates of 9007 and 9008 near to the points as shown in this figure. And then we can calculate the delta E value, the difference of easting, coordinates between 9007 and 9008, and delta N, the difference of northing between 9007 and 9008 control points. So this WCB from GPS coordinates of control points easily can be taken as beta angle. So the tan beta is equal to delta E upon delta N. So we can get the easting coordinate difference by deducting the easting coordinate of 9007 from 9008, and we can get the delta N value by deducting the northing coordinate of 9007 from the northing coordinate of 9008. Then the value is 0.193652. So when we get the tan inverse value, the beta is 10 degrees, 57 minutes and 35.28 seconds. Now you see the calculated WCB from the traverse is 10 degrees, 57 minutes and 57.04 seconds. But the actual one is 10 degrees, 57 minutes, 35.28 seconds. So the difference is the angular misclosure. So the angular misclosure is the difference between the calculated WCB and the actual WCB. So it is 0 degrees, 0 minutes and 21.76 seconds. So the next thing is we need to see whether this misclosure is within the permissible range. For that, so I have taken this from other Bannister's book 2013. Accordingly, for the engineering surveys, 10 root 10 seconds is the permissible range that the error can be distributed. So n means the number of stations used for the traverse activity. N is the number of stations used for the particular traverse. Accordingly, we can see the permissible error is 10 into root 5 seconds. It is 22.36 seconds, which is greater than 21.76 seconds. So it is just within the acceptable limit, and then therefore the error can be distributed like this. So the correction is negative if the angular misclosure is positive. The correction is positive if the angular misclosure is negative. Angular misclosure is positive for this example, therefore the correction is negative. So we need to deduct 0 degrees, 0 minutes and 21.76 seconds, and should be distributed cumulatively for closed link traverse. So you need to remember, in closed loop traverse we don't need to distribute it cumulatively, but in closed link traverses we need to distribute it cumulatively. So the angular correction for line 1 is the total correction value multiplied by the particular number of stations and divided by the number of used stations. So we used 5 stations. The first value is minus 0 degrees, 0 minutes and 4.35 seconds. Similarly, we can obtain these corrections for all the 5 stations we used to set up the instrument. So these are the corrected WCBs after deducting the cumulative corrections. So accordingly, we can tabulate it like this. So once we have these corrected WCBs, the next thing is we need to find out the linear misclosure. For that, we need to calculate the coordinates. The whole circle bearing of a line is measured in a clockwise direction in the range of 0 to 360 with reference to the magnetic meridian. Accordingly, we can find out the signs for the quadrants, right? So if our traverse leg is in the first quadrant like this, so all the trigonometric proportions you find is positive. So we can get the northing coordinate of OP line. The equation is OP cos theta. From OP cos theta, we can get the northing coordinate of OP line at the P point with reference to the origin, right? An easting coordinate can be taken from OP sin theta. So this theta is measured from north. So we can get the easting coordinate of point P measured from 0 with respect to the origin. So that is OP sin theta. So now you see all the sin theta and cos theta values measured in clockwise direction from the north are positive in this first quadrant. In the fourth quadrant, only the sin values are positive. In the third quadrant, only the tan values are positive and both sin and cos values are negative, right? And then in the second quadrant, only the cos values are positive. When you take the OP cos theta, it is positive, OP sin theta negative. Remember, these angles are measured clockwise from the magnetic meridian. Now we can find out all the partial coordinates L cos theta and L sin theta for particular lines. When we are calculating these partial coordinates, always we consider the origin is 0. From that means now 9003, 9004 line, eastern and northern coordinates of 9003 is 0, 0. And with respect to that 0, 0, we can find out the coordinates of 9004. Accordingly, the partial coordinate for the 9004 measured from 9003 is 52.672, and L sin theta, that is the eastern coordinate, is minus 44.243 meters. So that is how we find out the partial coordinate. Similarly, from all corrected WCBs for the whole circle bearings, you can find out these partial coordinates. So the lengths are given, the WCBs are given, these lengths are OP, and these, so the WCB is the theta. So the L cos theta and L sin theta can easily be found, and we can complete this table. When we get the addition of these all partial coordinates, it should be the actual difference between the GPS control points from 9003 to 9007. So this is 161.175 meters. The sum of all the easting coordinates are 31.587 meters. So we'll see we are getting the same difference from actual coordinates obtained from GPS points. So the actual northing coordinate difference between 9007 and 9003 is 161.181 meters. The actual easting coordinate difference between 9007 and 9003 is 31.583 meters. So the error in northern direction is calculated northern difference minus the actual northern difference. Now you see the calculated northern difference is 161.175 meters. The actual one found from the coordinates of GPS points, it is 161.181 meters. So there is a 6 millimeter error, but it is in minus direction. The error in eastern direction is calculated eastern difference minus actual eastern difference. So calculated one is 31.587. The actual one obtained from GPS coordinate is 31.583 meters. So the difference is positive, the plus 0.004 meters. So we can draw it like this. So actual 9007 is like this, but this is what we obtain from the traverse calculation. So there is a shortage of 0.04 millimeters in the west and 0.006 meters in the north direction. So then using the Pythagoras theorem, we can find the linear misclosure by getting the addition of squared value of delta n and delta e, the errors obtained in northern direction and eastern direction. So accordingly, there is an error of 7.2 millimeter. So the correction to the northern difference is 0.06 meters, that is a positive value. The correction is positive, and correction to the eastern difference is minus 0.004 meters. So the error is minus 0.006 meters. Therefore, the correction has to be positive. Since the error is negative, the correction has to be positive. Therefore, the correction to the northern difference is 0.006 meters. Since the error in the eastern direction is 0.004 meters, the correction to the eastern difference should be minus, negative. Because the error is positive and the correction is negative, it is 0.004 meters. So then we need to find out the allowable linear misclosure for the traverse. For that, we need to get the addition of all the traverse legs which were used for the traversing. So we use 5 stations, 4 legs, except these 2 control lines. So we don't take the lengths of control line to the traverse length. So all the other lengths except the control lines can be taken as the traverse length. So when we calculate all these lengths, the addition is 262.531 meters. For engineering surveys, the error for the unadjustable horizontal distances should be 1 meters in 10,000 meters. So we can find out whether our error is within that limit. So we have a closing error of 0.0072 meters for the length of 262.531 meters. So we can find out the error per meter. It is 2.7 multiplied by 10 to the power minus 5. So the allowable error for the engineering survey is 1 is to 10,000. It is 10 multiplied by 10 to the power minus 5. So already 10 into 10 to the power minus 5 is greater than 2.7 into 10 to the power minus 5. Hence okay. Therefore we can distribute the error using Bowditch rule. What is the Bowditch rule? In the Bowditch rule, we distribute the error as a fraction of a total length. As you see, the correction to the eastern difference is the total correction multiplied by the length of that particular traverse leg where the correction is added upon the length of traverse. So the length is the 262 meters, 531 meters, that is the length of traverse. Similarly, the correction to the northern difference is the same. The total correction multiplied by the length of that particular traverse leg divided by the length of the total traverse. So if the delta E or delta N value is negative, the correction should be positive. If the delta E or delta N value is positive, the correction should be negative, as we discussed earlier. For the correction for 9003, 9004 line can be written as 0.006 multiplied by 68.788 meters, that is the length of that particular traverse leg, and divided by the total traverse leg 262.531. So it is 0 plus 0016 meters. So we can write this up to 4th decimal place. If you preferred, or you can round off it to 3rd decimal place. So I prefer to write it up to the 4th decimal place. So the delta E correction is similar to that, minus 0.004 multiplied by 68.788 meters, that is the length of the particular traverse leg, and divided by the total traverse length 262.531. The answer is minus 0.0010 meters. So now we can tabulate all these like this. So all the corrections and to the delta N and all the corrections to the delta E can be tabulated, and then the corrected delta N and delta E can be tabulated like this. What we need to do is we need to add all these corrections to the partial coordinates you found by putting the equation L cos theta and L sin theta, and write in the corrected delta N and corrected delta E columns. Then what we need to do is we need to add the corrected partial coordinates, that means corrected delta N and corrected delta E, to the northern and eastern coordinates of 9003. Why? In calculating these partial coordinates, always we thought that the starting coordinates of that particular line is 0. So as an example, for line 9003, 9004, we assume in that calculation the coordinates of 9003 is 0. But actually there is a coordinate for 9003 that is written in this first column in red color. So we need to add the partial coordinate we found for 9004 to that previous coordinates, that means the coordinates of 9003, to get the actual coordinate of 9004. So for that we add the partial northern coordinate of 52.674 to the northern coordinate of 9003, and we can put it in the column of northern in front of 9004 station. So similarly we can add the eastern coordinate of 9003 to the corrected partial coordinate of 9004 and write it in the eastern column. Similarly, we can add the partial coordinate to the previous coordinate we found and fill these columns like this. Finally, after doing this calculation, you should get the same control point coordinates of 9007, because you need to end the traverse from 9007. So you should get the same actual GPS coordinates after distributing the error. So that's how we do a close link traverse using a total station. So in the total station, we can easily find out the included angles, and not only that, we don't need to use the tape to find out the length of traverse legs. So easily we can use the HD option and find out the length of the traverse legs, and then using this calculation we can find the coordinates of all these traverse stations. Once we found these coordinates, these traverse stations will become secondary control points. Thereafter what we need to do is we need to orient the instrument at these traverse stations or the secondary control points and collect the details with respect to the calculated coordinates. So that is how we are doing a closed link traverse. So thank you very much for watching this video. Coming up next is all the important operations of top cone total station. Don't forget to subscribe this channel and click the bell button for more of the very latest videos.